252 million years ago, the world began to die. It didn't happen in a single night, or even a single year, but over an agonizing span of millennia, an invisible executioner seeped into every ocean current and every breath of wind. It began in what is now Siberia, where a crack in the Earth's crust unleashed one of the largest volcanic events in the planet's history. For hundreds of thousands of years, molten rock poured across the land in waves as high as mountains, covering an area larger than modern Europe. But the true killer wasn't the lava, it was what came with it. Vast clouds of carbon dioxide and methane smothered the atmosphere, turning the air toxic, cooking the planet from within, and driving the oceans toward a suffocating stillness. Coral reefs vanished. Forests turned to ash. Entire ecosystems collapsed in a cascade of extinction so complete that it erased more than 90% of all life. This was not just a bad day in Earth's history. It was the Permian-Triassic extinction, the Great Dying. And it all began with a chain of events so relentless, so inescapable, that life itself nearly ended forever. 252 million years ago, Earth was a very different place. The continents we know today were fused into a single colossal landmass called Pangaea, an endless stretch of terrain that carried climates ranging from searing deserts at its center to lush, swampy forests along its coasts. Vast conifer-like trees reached skyward, seed ferns sprawled across the ground, and in the humid undergrowth, dragonflies with wingspans the size of hawks darted between fern fronds. The oceans, which covered nearly 3/4 of the planet, brimmed with a dazzling variety of life: coiled ammonites, trilobites crawling along the seabed, and brilliant reefs made of strange sponge-like organisms. On land, the ancestors of mammals, called synapsids, grazed and hunted across sprawling plains, sharing their world with reptilian predators and swarms of insects. The Permian world was vibrant, balanced, and stable, or so it seemed. Deep beneath the surface of what is now Siberia, an ancient pressure cooker was reaching its breaking point. For millions of years, molten rock, magma, had been pooling in vast chambers within the upper mantle. Driven by tectonic forces and fueled by heat from the planet's interior, this molten mass pressed upward, fracturing the crust with immense force. When the pressure finally became too great, Earth split open. What followed was not a singular volcanic eruption like modern humans might imagine, but a geological assault on a scale almost beyond comprehension. Towering fountains of lava surged skyward, spilling across the land in rivers that swallowed entire landscapes. The air itself vibrated with the roar of gas explosions, the hiss of molten rock hitting water, and the deep, unending rumble of the earth tearing itself apart. These were not short-lived events. Measured in hours or days, they lasted years, decades, centuries. The Siberian Traps, as geologists call them today, were born. Layer upon layer of dark basalt spread outward, hardening into the staircase-like formations that inspired their name. Over the course of hundreds of thousands of years, these lava flows would bury more than 2 million square kilometers, an area larger than all of Western Europe, beneath hundreds of meters of rock. But the true danger was not simply the molten rock. Every eruption sent vast plumes of ash, dust, and volcanic gases into the skies. Sulfur aerosols reflected sunlight back into space, plunging the planet into brief but severe volcanic winters, where frost crept over once tropical forests and crops withered. But as each cold spell passed, the relentless spewing of carbon dioxide from the magma tipped the climate in the opposite direction. The Earth warmed, slowly at first, then with terrifying acceleration. Over time, global average temperatures rose by up to 10 degrees Celsius. Inland regions dried into cracked wastelands where nothing could grow, while coastlines became stifling, humid ovens. Rain, when it came, was laced with acid, stripping leaves from trees and leaching vital nutrients from the soil. The oceans fared no better. Warmed from above and suffocated from below, their oxygen levels dropped until enormous dead zones formed, vast stretches of lifeless, stagnant water. In these poisonous depths, certain bacteria thrived, producing hydrogen sulfide gas that bubbled up to the surface and leaked into the atmosphere, further poisoning the air. The gas also shredded Earth's ozone layer, allowing deadly ultraviolet radiation to flood the surface. Life, assaulted from every direction, began to collapse. Coral reefs dissolved. Shell-building marine species found it impossible to survive in the increasingly acidic seas. Entire groups of fish and plankton vanished, breaking the food chain at its foundation. On land, forests died in waves, taking with them the herbivores that fed on their leaves, and in turn the carnivores that fed on them. Even insects, creatures that had weathered countless past extinctions, were not spared, suffering a catastrophic drop in diversity. This wasn't a single moment of disaster, but a drawn-out, suffocating decline. For tens of thousands of years, ecosystems tried to recover, only to be struck down again by the next pulse of volcanic fury. The Permian landscape that had once been so full of sound, the calls of animals, the rustle of leaves, the splash of fish, grew eerily quiet. By the time the last of the lava cooled and the atmosphere began to clear, more than 90% of all marine species and 70% of all land-dwelling vertebrates were gone. The Great Dying had erased entire evolutionary lineages from the planet forever. What was left was a battered, stripped-down biosphere, populated only by the hardiest and most adaptable survivors. The age of the Permian was over, and the world that followed would be entirely different, shaped not by the grandeur of what had been, but by the scars of what had been lost. The story of the Great Dying is not passed down in myths or carved into temple walls. It is locked inside the earth itself, written in lava flows, ash layers, and chemical traces so faint they can only be read with the tools of modern science. In the wind-swept highlands of Siberia, geologists stand among vast stair-like cliffs of black rock, each step a frozen wave of molten basalt that once rolled across the land. These formations, called the Siberian Traps, stretch for hundreds of kilometers, and in places the rock lies stacked more than 3 kilometers thick. When dated with radiometric techniques, these layers reveal something staggering. The bulk of this volcanic outpouring erupted in less than 1 million years, an eye blink in geological time, perfectly coinciding with the abrupt end of the Permian period 252 million years ago. But dating the rock is only the first clue. Inside tiny, glass-like crystals, scientists find microscopic bubbles of ancient air trapped when the lava cooled. Analyzing their contents, they discover greenhouse gases, carbon dioxide and methane, in concentrations far beyond anything in the previous tens of millions of years. These gases are planetary heaters, able to raise global temperatures by several degrees, and when released on such a scale, they would have thrown the climate into chaos. Yet the evidence is not confined to Siberia. Across the world, from the deserts of China to the mountains of South Africa to the red rock plateaus of North America, geologists find the same thin, distinctive layer in the sediment. A global ash band enriched with volcanic elements like nickel, mercury, and arsenic. Its chemical fingerprint is unmistakable, and it is laid down at exactly the same time in every location, proving that the Siberian Traps' poison circled the globe. In ancient seabeds that have since turned to stone, the chemistry of the sediments tells a parallel story. Oxygen levels plummeted. The oceans became acidic and stagnant, and entire marine ecosystems collapsed. These changes are revealed by shifts in the ratios of certain isotopes of carbon and sulfur, subtle atomic variations that act like signatures of environmental catastrophe. The fossil record mirrors the chemical record with grim precision. In layers from before the catastrophe, paleontologists find rich communities of creatures, trilobites, brachiopods, ammonites, and a riot of plant life along the shores. Then, abruptly, diversity vanishes. Species that had survived for hundreds of millions of years disappear without a trace, replaced, after a long gap, by a handful of hardy, opportunistic survivors. Even insects, the champions of evolutionary endurance, suffer catastrophic losses. Whole orders are wiped out, something almost unheard of in their 400 million year history. Still, questions remained. Lava alone, no matter how vast, might not be enough to kill almost everything. The answer lay not just in the volcanoes themselves, but in what the lava flowed over. In the Permian, the region that is now Siberia was rich in thick deposits of coal, oil shale, and other carbon-rich rocks. When the searing lava hit these deposits, it ignited them like a torch to a powder keg. The burning released vast clouds of carbon dioxide, methane hydrates, and sulfur dioxide, alongside black soot that darkened the skies. Sulfur dioxide cooled the planet briefly by reflecting sunlight, while the greenhouse gases trapped heat for tens of thousands of years afterward. A deadly 1-2 punch of climate whiplash. The soot and ash choked photosynthesis, starving plants and the creatures that depended on them, while acid rain burned through forests and poisoned freshwater systems. Layer upon layer of evidence, drawn from rocks, fossils, and isotopes, built the same picture: a world battered by volcanic fury, smothered in toxic gas, baked in heat, drowned in acid, and deprived of oxygen, until 9 out of 10 species on Earth simply ceased to exist. The Earth did not recover quickly. Ecosystems took millions of years to regain their diversity, and the Triassic world that emerged was alien compared to the lush Permian that came before. It is a crime scene from deep time, with the Siberian Traps as the prime suspect, and the geological record as the silent but damning witness. When the Siberian Traps finally went silent and the skies cleared enough for sunlight to once again reach the ground, the world they illuminated was unrecognizable. Gone were the lush Permian forests, the teeming reefs, and the intricate food webs that had taken hundreds of millions of years to weave. The continents were quiet, bare in many places except for stretches of scrubby vegetation clinging to poor ash-laden soils. The oceans were equally barren, their surfaces strangely still without the constant churn of life that had once filled them. It was not simply that species had died. Entire ecological roles had vanished, leaving gaps in the planetary machinery of life. The early Triassic was an age of survivors and opportunists, creatures that could endure extremes of heat, drought, and scarcity. In place of diverse forests came thickets of hardy lycopods and seed ferns. In the seas, strange, disaster-tolerant bivalves and a handful of ammonite species became the dominant players. On land, the great synapsid reptiles that had ruled the Permian were reduced to a few struggling lineages, many small and unremarkable. With so many predators gone, ecological niches stood empty for millions of years, inviting new experiments in evolution. But recovery was painfully slow. For nearly 5 million years, biodiversity remained at a fraction of its former level, a stretch of time longer than all of human history. The climate swung wildly, with intense heat trapping the planet in what some scientists call a hothouse Earth state, driven by the lingering greenhouse gases unleashed during the eruptions. The poles were ice-free, the tropics blisteringly hot, and seasonal droughts and floods battered the fragile ecosystems struggling to re-establish themselves. Yet, in this crucible, life's resilience began to assert itself. In the oceans, new groups of reptiles, the first ichthyosaurs, took to the water, sleek-bodied and swift, filling roles once held by vanished predators. On land, the archosaurs, distant relatives of crocodiles and birds, began to diversify, laying the groundwork for the rise of the dinosaurs. Plants evolved new strategies to cope with heat and aridity, spreading seeds that could survive long dormant until the right conditions returned. Each innovation added a thread to the torn fabric of life, gradually weaving back complexity. But the story of the Great Dying is not just a chronicle of destruction and recovery, it is a warning written in stone. The chain of events that began with the Siberian Traps shows how interconnected Earth's systems are and how quickly those connections can unravel when pushed beyond their limits. The massive release of greenhouse gases, the rapid warming, the collapse of ecosystems, the acidification of the oceans, all have eerie echoes in the changes scientists observe today. In a sense, the Permian-Triassic extinction was a preview of what can happen when climate shifts faster than life can adapt. Except that in our time, the trigger is not a volcanic cataclysm, but our own industrial activity. The rocks of Siberia stand as both a monument to the planet's capacity for catastrophe and a testament to life's stubborn endurance. They remind us that Earth will recover in the long run. But the question for our species is whether we will be among the survivors, or one more layer in the sedimentary record of a future geologist's dig. The Great Dying ended more than 250 million years ago, but its shadow still stretches across our understanding of life's fragility. In the strata of rock, in the chemistry of ancient air trapped inside crystals, and in the fossilized remains of vanished worlds, the message is clear. No matter how dominant or complex life becomes, it exists at the mercy of Earth's changing systems. The Siberian Traps were not just a geologic event. They were a planetary reset button, wiping away the vast majority of species and forcing evolution to start over with what little remained. The survivors, small, adaptable, and often unremarkable, became the architects of the next great chapter in life's story, proving that persistence, not power, determines who inherits the future. Recovery took millions of years, and the new ecosystems that emerged bore little resemblance to the ones that came before. In that transformation lies a sobering truth. Extinction is not the end for Earth, but it is the end for the forms of life that fail to adapt. The Permian-Triassic extinction is often seen as an alien event, locked in the distant past, but the processes that drove it, runaway greenhouse gases, rapid warming, ocean acidification, and the collapse of biodiversity, are not alien at all. They are mechanisms we are now recreating, not through lava and fire, but through the combustion of fossil fuels and the release of carbon at a geologic scale, compressed into a human lifetime. The difference is that in the Permian, there were no species with the awareness to read the warning in the rocks. We are the first to see the pattern, the first to understand the stakes, and perhaps the first to choose whether to continue the trajectory or alter it. The Siberian Traps remind us that Earth will endure regardless of what happens to us, and life will return in some form. But the continuity of the world we know, the forests, the oceans, the climate stability that allowed human civilization to flourish, is not guaranteed. It is a temporary arrangement, one that can be broken as easily now as it was in the Permian. The lesson is both humbling and urgent. We live not outside the forces of deep time, but within them, and the same chain reactions that once reshaped the planet still exist. waiting for a spark.